Okay, so vertical asymptotes. Now, we've already studied these in pre-calculus, right? You know that without the graph here, you should be able to determine, if you just looked at that function, there's a vertical asymptote at x equals 1, right? Any zero in the denominator, provided that same zero doesn't exist in the numerator, which I'll talk about in a second. You might remember that's a whole. Then there's a vertical asymptote, right? What's the connection? Well, the limit as x approaches that value, right? The limit as x approaches 1 does not exist because it's unbounded. Or we can do it from the right down to negative infinity, right? And that's how we can redefine vertical asymptotes using calculus, using limits. So no big deal, right? You kind of already know how to do this. If I ask you to find a vertical asymptote, then I don't care how you do it, right? But make the connection to infinite limits and vertical asymptotes. But again, I'm just going to say, let me jump down ahead. Like, here's a function, 1 over 2x plus 1, find the vertical asymptote, right? So it should be pretty clear. Say, oh, wait, there's a vertical asymptote at x equals negative 1, right? As long as there is a 0 in the denominator, and that doesn't exist in the numerator, then it's a vertical asymptote, right? And you can extend that to the calculus. The limit as x approaches negative 1 does not exist. From the left, from the right, it'd be up to infinity or down to negative infinity. Okay, so let me jump back. That's all this slide is saying here. Again, I got to talk about this part in a second. That's the whole scenario. And again, this is just the vertical asymptote definition. Let f be continuous on the open interval. This is actually the old definition. It doesn't have the limit in there, right? But is basically what it's saying. If g of x equals 0, exists an open interval, let f be continuous. If if there's some value that makes the denominator 0, that's a vertical asymptote, provided that that is not true for the numerator. Okay, so let's try and make sense of that. This one, pretty clear. Let's just say, as for vertical asymptote, x equals negative 1. Easy. Well, how about this function? What if I said, tell me what the vertical asymptotes are? Okay, that's really a pre-calculus question, but we can extend it, like I said, to limits. Now, be careful, because you might take a look at that denominator and say, well, wait a minute, there's 2 zeros in the denominator, one at positive 2 and one at negative 2, so those are both vertical asymptotes. But be careful, and this has to go, this deals with what I was talking about before, the numerator not being 0. But in this case, there is a factor in the numerator that where the x equals 2 is both, gives you a 0 in the bottom and a 0 in the top. So there's not a vertical asymptote there, right? When you get close to x equals negative 2, you do have a vertical asymptote based on that definition, because there is not a like factor in the numerator or of x plus 2, or there's not a 0 of x equals negative 2 in the numerator. So that's a vertical asymptote. But you can see the idea behind it. Think about what happens as you get close to negative 2. For example, negative 2.1. Negative 2.1 plus 2 is negative 0.1. So you divide it by a small number. So you get that asymptotal behavior. But what about when you get close to 2? Why is that not a vertical asymptote? So let's say I put 2.1 in here. What happens? 2.1 divided minus 2 is 0.1. So wait a minute, I'm dividing by a small number. Isn't that asymptotal behavior? But it's not, because as you get close to 2, you have that same small number up here, right? So those guys are really canceling each other out, and you end up with a hole there, which you might remember from pre-calculus. So you only have one vertical asymptote. How do I extend that to calculus? Well, the connection, of course, is what happens as I go negative 2 for this function, f, and maybe I say from the right. So what's the answer to this? So that'd be good practice. So we don't have to worry about these two guys. They're going to cancel out. We got a positive here. So all I have to do is figure out what happens as I approach negative 2 from the right. What's to the right of negative 2? So you got to be careful. A number to the right of negative 2 would be negative 1.9, not negative 2.1. Right? To the right of negative 2, greater than negative 2 is negative 1.9. So that means when I plug that in, that's a positive. That's a positive. I can ignore those guys. They're canceling each other out. So we know that that's going to be going to positive infinity. Okay, so those are basically the two things we're studying in this section. Limits at infinity, right, as I get close, and those can also be vertical asymptotes. What do you think about this one? Find the vertical asymptotes. Well, this does not factor. In fact, x squared plus 1 never equals 0. So that means I have a vertical asymptote here and a vertical asymptote here, right? I had to get that behavior in both cases. That's it, right? And again, the calculus piece would be find the limit as x approaches 1 from the left of this function that we're calling h. Okay, and then that's either going to be positive 50-50, positive or negative infinity. You just have to kind of reason it out. What else do we have here? Why is that not working? 1. Okay. All right. Let's see. We did that one. Let's talk about this. Okay. So let's talk about more complicated ones. We didn't really call this a rational function before, but you might remember some of your trig functions. In fact, 4 out of the 6 have a whole bunch of asymptotes. The tangent function is, by the way it's defined, has defined as a quotient. Y over x or sine x over x is going to have a bunch of places where you're dividing by 0. Same thing with your cotangent function. Cotangent, one way to look at it is cosine over sine. So what we're saying here is everywhere where the sine x equals 0, you're going to have a vertical asymptote, right? Because there's no cancellation going on in these functions. There's no like factors. So whenever the sine is 0 for your cotangent function, based on how we can define it as cosine over sine, then you're going to have a vertical asymptote. So you should know where the sine equals 0. That's going to be at 0. All right, sine of 0 is 0. Sine of pi is 0. Sine of 2 pi is 0. So that means you have vertical asymptotes there. Okay. And in fact, you can categorize that or abbreviate that or state that there's a vertical asymptote every n times pi. That's when sine x equals 0. That's where cotan x has a vertical asymptote. And again, bring in the calculus piece. Find for me the limit of the cotangent of x as x approaches 0 from the left. What does that equal? Well, you have a graph here, which graphs make this really easy. So I come into 0 from the left, this goes up to infinity. What if I didn't have a graph? Well, you just had to kind of think about this as that's a 0. As you get really close to 0 from the left, what's the cosine function do? Well, that's actually getting close to 1. That would be about 1, right? Remember your cosine curve goes like that. So as I come into 0 from the left, I'm up here at 1. What happens cosine x over? So this is just me trying to figure it out without the graph. What happens as sine x approaches 0 from the, oh, I'm sorry, I said from the left. I should be. The answer for cosine is the same. As I come in from the left, you're up here at plus 1. That's the same for both. But the sine, that would be important. Your sine curve goes like this, right? So the question is, what's your denominator doing, right? As the sine, as I come into 0 from the left on my sine curve, I'm down here at a really small negative number. I don't know, something like that. Right? So that should support, I might have done it backwards. As I come in cotan from the left, I should be saying, I think I came in from the right. From the left, this guy goes down to negative infinity. And this method supports that, right? Something going to 1 divided by something going to 0, but on the negative end, then that should also go down to negative infinity. Okay, so we need to be able to do this thing with or without a graph. And here are some properties. You've studied properties of limits before. These ones should sort of make sense. So let me explain this. We have one limit that's infinite and one limit that exists. Okay, so as you come into C, then if one guy is infinite, what happens if you're adding or multiplying by another limit that actually exists? We'll call it some constant L. Well, if you think about it, adding an L to something that's unbounded, the L doesn't matter, still unbounded. Same idea with a product. So this G has a limit, right? Just some number, that's just some number, and this guy's unbounded. So if G's positive and F goes to infinity, so does the product. If G's negative, right, the limit as x approaches C is L. If L's negative, I should be saying, then that product goes down to negative infinity. Okay, and then this one is something that we've talked about before, you've seen before. If the denominator is blowing up and the numerator is fixed, then your whole function goes to 0. Okay, so let's look at a couple examples. I got the answer for the first two, so let's see if that makes sense. Well, the idea is that you can break this up, right? I can go to 0, 1 plus the limit of 1 over x squared as x goes to infinity, right? And that's the property we talked about before. If I have a constant here and the denominator is going to infinity, 1 divided by infinity is 0, right? And then this one, that's just a real basic limit. If the function's 1, it doesn't matter where x is going, the function's always going to 1. So this would be 1 plus, oh, I got this backwards. Hang on, let me backtrack real quick so I don't have to start my whole video over. Let me just, come on now. It's not letting me. Let's try this. Sorry, give me 1 second. This seemed to work last time. Okay. Restart. The limit as x goes to 0. This is one of my properties. You get the sum of two limits. One of them's unbounded. I got this back. I put an infinity there. That's why I had a mistake. So let's try that again. As I go to 0, if my function's constant, then I'm staying at 1. Now, what happens with this one? Well, I'm dividing by 0, right? So this is an infinite limit. So this one should be infinity. Now, this is one of those cases where the limit as x goes to 0 from the right of 1 over x squared is the same as it's from the left, or if it's just 0, because the bottom's squared. That's everything's going up, right? That's a vertical asymptote. So 1 plus infinity is still infinity. Okay. Let's see. Why is this one 0? Let's come back to that one. That one's probably the most complicated one. And let's talk about the A. We'll skip B for now. And we'll do this one as I come into 0 from the left. That's 0 plus what happens to the limit as I come into this guy from the left. Well, we could do this a couple ways. You might know this is a real basic graph. Or you could just pick a small value like we've been doing, negative 0.1. And you can see 1 divided by negative will take you down to negative infinity. So 0 plus negative infinity is still negative infinity. How about your cotangent as you approach 0? So we just talked about that one in the last one. As I approach 0 from the right, here's your cotangent. It's going up to infinity. So that means 3, deleted all that. 3 times infinity basically is what we're saying here. That's still infinity. Okay, so I'm running out of time for this video. I'm limited to 15 minutes on my program. So go ahead and try that one. See if you can support why it's 0. If you have questions, go ahead and post them below.